Hello, it's Keith here, and this is the first in my series of 68,000 assembly programming tutorials. Now, just like I've done with the 6502 and the Z80, we're going to be looking in this series how to program 68,000 assembly language from beginnings on a variety of different systems using only free tools and resources. So we're going to be using VASM as with my other series for our assembly, and VASM's good because it supports all three processors, and that's especially important if you're going to program for the Neo Geo or the Genesis, because those systems have a secondary processor that is a Z80 for sound, so you might want to be able to program both chips with the same assembler, and VASM can certainly do that for you. Now, in this series, we're going to be doing 5 different systems: the Atari ST, the Commodore Amiga, the Genesis, the Neo Geo, and the X68000 by Sharp. And we're going to be using Steam for Atari ST, FSUAE for the Amiga, Fusion for the Genesis, MAME for the Neo Geo, and X68 High Speed for the X68000. But of course, if you're using a different system other than Windows, you might want to use alternative emulators. That said, I will be providing as best as I can the development tools that I use for this series. You may need to find your own ROM files for it, but you will be able to download the emulators, all of the build scripts, all of the tools I use to create disk images and so on, so that hopefully you can get these working at home the fastest way possible, so you can just really get into developing. It's my intention that with as little effort yourself as possible, you should be able to run simple programs so you can start learning and experimenting rather than figure out how to get things going. All of the source code for this series is going to be available for download from my website as well, and every single lesson that there's a video for, there will be a text-based companion on my website. So if you need to reread or you want more time to think about things, please check out the website for that. There's also going to be a cheat sheet of the assembly language commands so that you can quickly look things up if you forget what a command does, because we all do that. So let's start actually looking at how we're going to program things. This series is intentionally designed to be multi-platform, as are my other series. We're not just going to program commands that work on one system. We're going to work on all of the systems in a common way so that wherever possible our programs will run on all of the systems, and this is what I did for Grimes Z80, Grimes 6502 and Grimes 68000. That was 3 programs that ran on a wide variety of different systems, and the only reason there was 3 is, of course, they were different CPUs. So that's what we're going to be doing in this series. We're going to be writing generic code, especially with this beginners series. We're just going to be looking at basic 68,000 commands. When it comes to doing sound and graphics and hardware specific things, that will be covered in a later platform specific series on all of these machines. So that's what we're going to do there. Now, there is something important that the scripts that I use do in places need to know which system they're compiling for, and there's something called a symbol defined, and this is a text-based label that has a numeric value, and the assembly scripts detect this and then branch out to the platform specific stuff. So if you're not using my build scripts, you'll need to make sure you define the same symbols. So build AST for the Atari, build AMI for the Amiga, build Gen for the Genesis or the Mega Drive if you prefer, build Neo for the Neo Geo, and build X68 for the X68000. If you're using my batch files though, they define this automatically, so that will be something you don't need to worry about. Anyway, enough talk about the introduction. Let's have a look at something actually compiling. Now, if you choose to download my toolkit that I've uploaded to my website, you will be presented with an archive that extracts to this. And what you can do is you can click on this xdrive.bat file here, and what this will do is it will map a virtual X drive using the subst command, which is pre-configured with all of the tools that I use. And then you can load Notepad++ here, and you should have the development environment that I use with these tutorials. So hopefully that should be able to get you started up really quickly, assuming you're using Windows. Now, if you're not, you'll need to configure everything yourself, but as I've said before, VASM is available for Linux and the Mac. So if emulating a Windows machine isn't an option for you, then you can at least get things working that way. So here we've got a very simple program here using the move command. Now, the move command will transfer data from one place to another. In this case, we're using a fixed value and we're moving it into a register, but we can move a register into another register as well. So the important thing to notice here, if you're familiar with Z80, is the source is on the left hand side and the destination is on the right. In Z80 it's the other way around, but apart from that the command is pretty straightforward. And then we're going to jump to subroutine monitor. This final command here, jump star, jumps to the current line, which creates an infinite loop just to stop the execution. Now, monitor is a program I've written in a 68,000 assembly, and it will show to the screen the registers on the system. So I just want to show you now this running very quickly just to show you what we're kind of working with. So this is Notepad++, and I've got this configured in such a way that if I press F6, I get a build script option here, and this will run one of 5 batch files, or well, there's even a 6th one there for the Z80 X68, but we can just run this for the Amiga here. If I just get that into frame there, we'll speed it up a bit and type start. And you can see now we've done a monitor dump of the registers of the system. So this gives us a good opportunity to see the resources that the 68000 processor gives us. So you can see here we have registers marked D0 to D7. Now a register is a piece of tiny memory within the processor that stores values very, very quickly. Of course, you have extra memory outside the processor, but that's much slower. So we do all our internal maths with these registers, and then we call out to external memory when we need large amounts of data. So we have registers D0 to D7, and these are basic maths registers. You can imagine these like the accumulator of the Z80 or the 6502, and that's a very good comparison because on the 68000, all of these data registers are equal. Whereas the accumulator on the Z80 could do more than the B register or the X register on the 6502. On the 68000, every register D0 to D7 are completely as powerful as each other. We do, however, have some alternate registers. These are the address registers. These are numbered A0 to A7. These are used for reading data out of memory or writing data into memory, so they store addresses that we would like to read or write off from. If you think of the Z80, these will be like the HL or the DE register pairs. But as you can see on the screen here, all of the registers on the 68000, despite it being called a 16-bit processor, are actually 32-bit registers. They can work at 8-bit or 16-bit, but their full capability is 32 bits. This is especially unusual with the address registers because the address bus is only a 24-bit address bus. This means that addresses can go from 00000060 to FFFFFF. So the entire address range is 24 bits, but all of the registers are 32 bits. We'll come into this a little bit more. Now, one more thing I do need to say about the 8 address registers that are available to us is A7 has a special purpose. Now, you may notice there's something missing from this screen. You've got your program counter, which is the current running byte of the program memory. This is something that all of the processors have. But what you can't see there is a stack pointer. There's a good reason for that. A7 is the stack pointer. If you use SP in your code, then the assembler will convert that to A7. A7 and SP are both the stack pointer. That's a bit strange, certainly is, but there is another thing that's very unusual about the 68000 processor compared to the other systems we might have seen, and that is that all 8 of the address registers can function as stack pointers. There's no push and pop commands as such. There are other commands that we use, and those commands work equally on all of the other registers. So we can use A0 to A7 as 8 separate stack pointers if we had some crazy requirement to do so. But that's just something to just bear in mind for now. That we're going to cover that in later lessons. I just wanted to give you a full introduction to the functionality there. Now, as I say, all of these registers are fully 32-bit, but that doesn't mean we need to use them at fully 32-bit. We can treat them as 16-bit or 8-bit registers, and we're going to look at that later in today's lesson. So that's this very simple example running on the Amiga. Let's just see it on the Atari ST. And there it is. And here it is on the Genesis, much faster on the Genesis, and that's a good reason why we're going to be doing a lot of our testing in this series on the Genesis. Because the stuff we're going to be doing is based on the processor and not on the hardware, it really doesn't matter which one of these systems we do it on, it will work the same. So here is the Neo Geo version. And here is the X68000 version. So you can see that the examples we're doing today, because of the support assembly code I've written, can be run on all of these systems in the same way. Now, they won't, in today's example, give the same result in all cases, which is why we're only going to look at it on one system. And the reason for this is the memory on a 68000 system isn't as easy for us as a programmer to work with in some ways as a Z80 system or a 6502 system. On 8-bit processors, we pretty much have full control over the system, and we can take the memory wherever we want, do whatever we want, and as long as we don't ask the firmware to do anything again, it doesn't matter if we've trashed the firmware's memory, we don't need to worry. However, on 68000 systems, we have underlying operating systems and drivers. The processor even has 2 modes, a standard mode and a supervisor mode, and it has debugging tools and things that it can run that are kind of above our normal running code. So That's a bit of a tricky thing, and also what it means is we don't even know where our program will be loaded into memory on the final system. And so some of the examples today are using very crude addressing methods just as tests, and that may not work on all systems. So as I say, in some cases the examples today won't work on all systems because we're kind of doing things a bit aggressively, a bit crudely, just to get things started quickly. But as I say, in general, once we get past the early stages, all of the code will work on all systems, because we're only learning the commands for the basic 68000 processor, not the 68010 or one of the later processors. This is all going to work on any system that's 68000 based. It's just if we're writing data to a certain address space, well, that might be ROM on one system, it might be protected RAM on another. So in some cases it may not work on all systems, but generally it should. We're going to discuss those complexities of 68000 processors in the later lessons as well, so please don't worry about it yet. But today we're just going to be making a basic start. So you saw there I was able to get the programs loading on a wide variety of systems very quickly, and the trick behind this is a set of batch files I've written that will automatically compile and execute the program as far as I can manage to do so. So let's have a quick look at one now. Here's the one for the x68000 system. So you can see here we're using VASM here to assemble it, no surprise there. We're specifying the 68000 processor. We're checking for labels. What this means is if you accidentally forget the tab on the left hand side of the screen, your program command might be mistaken for a label. This will warn you and hopefully reduce the problems you have there. Then we've got a no case command to disable case sensitivity to make things easier for us. Here we're defining a symbol called VASM, which isn't actually used by my code. This was for the Z80 systems because I was using Win8 and VASM to assemble on those systems. We're exporting the entire assembled code to a listing file here. If you want to see the bytecode that each command converts to, this is where you can check it. It's occasionally worth doing because sometimes the assembler is optimizing our code. And then we're defining build x68. This is very important because this is what my multi-platform ASM files use to detect which system is being executed and which system assembly code needs to be added to support the platform that's going to be assembled for. Now this switch here defines that we're outputting an X file, which is the x68000 executable file. The author of VASM was kind enough to add x68 X file support to VASM so that I could develop for the x68 with it. And then finally we're outputting to a file with this name here. Now, unfortunately with the x68, that's not all we need to do. We do need to create a disk file and add in the program into it. So we're doing that here, and then we're starting x68 here. And the disk image that we're using is predefined to automatically load up a simple autoexec batch and then run the program. So that's all we need to do from this batch file. Now, if you're doing this on Linux or another system, you would need to create an equivalent batch file, and you'd need to find equivalent disk tools. Some of the other systems are much simpler. The Genesis is far easier. So if you're not worried about which system you're programming for, just pick one of the easier ones. But I wanted to show you how the batch files worked with regards to compiling for the systems. So we've seen the program run on all of the systems, so we have a basic idea of what we're going to be doing here. Now let's have a look at the structure of the code we're going to be looking at. So the examples we're going to be looking at here have a header, and this is this area here, and this is just doing the initialization before our program runs. They also have a footer, and this is at the bottom here, and this is loading in some more requirements. And you can see I've got a special little command here I've written today just to quickly show D0 to the screen to save some screen space basically. But we're not going to look at that today. We're just going to look at basic mathematical commands today. And we're not going to worry about what this footer stuff does here. This is all going to be covered in the platform specific and the multi-platform series that will follow this basic series. The basic series is just going to cover how to actually do simple mathematics and other processor-based commands. Now, I do want to tell you about some potential pitfalls that you might have using VASM and a lot of other assemblers, to be honest, that I was caught out by at the early stage. Now, you'll notice here there's a tab at the start of each of these lines. This is important. Something that's at the far left is a label or a symbol. You can see a label down here. These mark a line within the code that we may want to call or jump to. We're going to cover those in a later lesson though, but I did need to explain that. The important thing is if I forget the tab here and now I compile, there's a line here that says that the label name is conflicting with a command, and that's because it's been mistaken for a label when it's actually supposed to be a command. So what I need to do is just make sure there's a tab here. Now VASM has another rather interesting one that really threw me all over the place at first. You'll see now I've fixed that bug, I can compile just fine here. But if I put in a space just here, I'm now getting the error number or identifier expected, and that's quite odd really. And you know, maybe I'd like to tab align the second parameter or something, but VASM doesn't let us do it. So that's something that you really want to avoid, because it really drove me nuts. I thought I was using the wrong commands when I started programming 68000, because my code wouldn't work and the examples looked identical to my code. It was just because I got an extra space in there, but it doesn't say, "Oi idiot, you've put a space in." It comes up with this rather confusing, misleading explanation of that. So what did this command do? Well, what we did is we moved a long word, which is a 32-bit value, and we loaded hexadecimal 69 into D0 here, and D0 is of course our register. Now we're going to look at all of this a bit later, but for now just take that as read that that's what that did. And then we called the monitor, which is our test program, which will show all of the registers to screen so we can see what actually happened. So let's have a look at a more complex example now. So this time we're going to use registers D0, D1 and D2, and we're going to do 3 different loads of the value 69, but you'll see we've put different symbols at the start here. Here we've put a hash and a dollar, here we've put a hash, and here we're just going to put nothing. I've just taken some brackets out, but we'll explain those brackets in just a moment. So we're using the value 69 in all 3 cases, but there were some symbols missing or present at the start. And so what's actually going to happen here? Well, let's try it out, shall we? So you can see here the first line is value 69. These are all showing in what's known as hexadecimal. Hexadecimal is base 16. If you think of human being numbers as base 10, going from 1 to 9 and then moving up to 10, hexadecimal is base 16. It goes from 1 to 15 and then the next number will be 10. Now obviously that's a bit odd, but the way it works is that 10 is an A, 11 is a B, 12 is a C, 13 is a D, 14 is an E, and 15 is an F, and then 10 is essentially 16. Now, I'm not going to go into it in any more detail at this point. If you don't know what hexadecimal is, I've got another tutorial on hexadecimal already, so please look at that, look at the website, or just do some searching around at it. And if you want to ever play with hexadecimal, I'd suggest you use the Windows calculator, because it has a hexadecimal mode built in. You see, if I do 15 here in decimal, press hexadecimal, you see it converts to F. If I then do +1, it converts to 10, and you can see if I convert back to decimal, it is indeed 16. So if you're stuck with hexadecimal, and just please look it up yourself, either on YouTube or on my website, or just play with it in calculator, and even Excel can help you with it with its dec to hex command. So anyway, the first value is a hexadecimal value, hexadecimal 69. Now the second one is 45. Well, why is that? Well, if I put in 45 in hexadecimal here and click decimal, you'll see it's decimal 69. And you can see here we missed off that dollar symbol from the definition of D1. The dollar symbol means hexadecimal. So we've loaded in decimal 69 into D1. But what about D2? D2 is now 0. Well, I'll tell you, 69 with no hash is a memory address. What we've done is we've loaded from memory address 69 into D2, and memory address 69 was 0. Now, you saw me take those brackets off earlier, and you can, if you prefer, put brackets in here, and VASM will assemble that just fine. Often brackets are used in 68000 to denote an address, so for clarity you can do that, but you don't need to. There is, of course, an important point here. If you make a mistake and forget that hash symbol, you will load from a memory address. You see, I just took that hash off the hexadecimal 69, and if I run again, I'm now loading from memory address hexadecimal 69. And so you can see D0 now has a crazy value in it that's obviously the bytes at that memory address. So we need to be very careful when we put our commands and make sure that we put a hash in if we want a fixed number value. Otherwise, we're going to be reading from a memory address, either hexadecimal or decimal memory address. So that's something very important we need to do. Now, there are a few other ways of representing immediate values you might want to use. You can use the hash, of course, for a number, the hash and the dollar for a hexadecimal number. Hash and percentage can be used for a binary value. Hash and apostrophe can be used for an ASCII value. And of course we can use just a number on its own for an address, or a dollar and a number for a hexadecimal address. Now we're going to look at another example here. Now we looked before at using L with the move command to move a value into a register, but there are other options. We can use a W or a B as well. And what these mean are byte, word and long, and these are related to the fact that although all the registers are 32-bit, we may not need 32 bits. We may want to work at a lower definition, and of course this is faster. The less data we're moving around, the faster things are going to be. So we can specify B for a byte, which is 8 bits and gives us a value from 0 to 255. In unsigned numbers, if it was assigned a positive or negative number, it would be only minus 128 to plus 127, but we're not going to worry about that just yet. If it's a 16-bit number, then it's a word with a W, and that's from 0 to 65535, and a 32-bit number, an L, is 0 to 4.2 billion. The important thing to notice is there's no 24-bit number. You remember I said that the address bus is a 24-bit address bus, so if we're working with addresses we have to work at 32 bits even though 8 of those bits won't actually do anything. So what's this example going to do? Well, first we're going to clear all 3 of the registers here using the move command. We're going to move 0 into D0, then we're going to move D0 into D1, then we're going to move D0 into D2. So we've effectively cleared all 3 registers. Now this isn't the fastest way of doing things, but it's the only way we're going to look at just yet. So what are we doing next? Well, we're loading in 4 bytes of hexadecimal 69 into D0 just as a sort of marker there. And then we're going to copy a word, so 16 bits of D0 into D1. And then we're going to copy a byte, so 8 bits into D2. Then finally we're going to move 4 bytes of 77 into D3. And then what we're going to do last is we're going to do move without specifying what length we want to copy using D0 into D3, and we're going to see what happens when we fail to specify exactly how many bytes to copy. So we're going to run the monitor and see what all of these commands do. And here's the result. So D0 has been set to all 69s, as you can see here, because we specified we wanted to work at the long range here. And then when we specified a W here, we've only moved 2 bytes here, which is what we'd expect. Now notice here that the top bytes are 0 because we cleared all of the registers here before, but it's very important, very, very important on the 68,000 that if we don't clear all of the bytes, we have no guarantee what the top bytes will be if we only copy a byte or a word. I'm saying this is very important because it caught me out a lot of times. If you do some commands at the B level and other commands at the W or L level, you will find that your commands are malfunctioning. So make sure you either do everything at the same level or you clear at the long level first. So that's something we're just going to discuss now. We'll come back to it later because it is so important. So anyway, so we've successfully copied hexadecimal 6969 with that W command, and this B command has copied just 69 here, and all of the other bytes are 0 because we cleared them here, not because we can rely on that. Now we can see a very good example of this here. We filled D3 with all 7s, so it should be 7 all the way along here, but then we did a move command here and we didn't specify what we wanted to do. So we just said copy D0 to D3, and that's what's happened here, and it's worked at the word level, so it's worked at 16 bits because we didn't tell it what to do. So this is something quite important. We can specify the exact size to work at, or we can just omit it, and the assembler has compiled using the 16-bit command. But I'd strongly recommend you always specify the length you want to work at, because if for no other reason it will reduce the number of mistakes you make with regards to what I just said of forgetting how many bytes are clear or safe within the registers, because if you always work at the byte level you'll have no problems, but if you forget one time and work at the word level you might have corrupt data in the remaining bytes of the register. Anyway, you can see here that the move command will work at long word, at word, or at byte level here. Now that's not always true of all commands. Some commands can only work at one level, some commands can work at all 3, but it does depend on the command, and that's why I suggest you have a look at that cheat sheet on my website if you really want to see all of the details of the commands and which commands can work at which levels. So there we go. Now we've just looked at the move command, and in some ways it's a good thing, in some ways it's kind of a bad thing, but the assembler is actually helping us out quite a lot here, and it's doing things that we haven't asked it to that really we should have done ourselves. So what I want to do now is discuss some of the quirks of 68,000 assembly and why the assembler is really doing us a big favour here. Now this is something you can ignore, so please, if you get confused over the next bit, just forget about it, but we do need to discuss it if I'm going to do a proper tutorial on the 68000. So we just used the 68000 move command and we moved various values around, and that was just fine. But technically there are some alternate versions of the move command that can do other jobs. Now you see we've used this move-L command here to move a value into a register, but that's fine with the D0 to D7 registers, the data registers, but technically speaking, when we work with an address register, we need to use a different command. We need to use the move A command for address register, and let's just see that in action here. So you can see here we've moved hexadecimal 69, 69, 69, 69 into address register 0, and of course that's worked just fine. But that's only technically speaking, because actually the assembler is quite willing and able to do the work for us. If we take the A out, this will still compile just fine, and you can see it just works fine. Now technically speaking, we've used the wrong command, but the assembler is so smart it's done the work for us. And the beautiful thing about this is there's no disadvantage to this. It's not that we're using a slower command. The command is actually the exact same. The assembler knows the move command can't do that, and it has used the move A command instead for us. So that's something that the assembler has done for us automatically. Now there are a few other quirks, interesting commands that it's worth us looking at, and another one is the move Q command. Now move Q is move quick. This moves a value from -128 to +127 into a register, and it only works at the long level. So there's no move Q B, that doesn't exist, but you can move the long in there. And the reason it's quicker is it compiles down to just 16 bits, whereas the normal version would be much larger, having an extra value. We're not going to look at that in too much detail, but just take my word for it, it is quicker. Now again, actually the assembler will work out where we could have used this command and use it automatically for us if we don't. So if we just said move L #01, now I've actually checked the output of the VASM assembler, and it does detect that we should have used the move Q command, and it does it for us. But just for clarity, I will be using the move Q command in these tutorials, because the move Q command is a much faster command, and so we do want to use it if we can, and we want to be clear about when we're trying to use it. Another interesting command is the clear command. Now the clear command is effectively setting a register to 0. And unlike the move Q command, which would arguably be the same if you were moving just to 0, the clear command works at bytes, words or longs. So you can clear just the last byte of a register using clear B, or the last word using clear W. So the clear command is another way of doing things more quickly than moving a 0 into a register. Now VASM does not compile a move 0 to the clear command automatically. I believe there's some quirk with the 68000 processor that means that in some special cases it may not actually be an identical swap out. I don't think it's ever going to cause us a problem in the series we're doing here, but that's I believe is a technical limit. There's some kind of quirk with the 68000 processor. Now the 68010 and later, it will convert to the clear command according to the documentation, but that's only a technicality. I don't want you to get too worried about that. The important thing I'm trying to say is we will be using the clear command because it's faster, and the assembler won't help us out with that. We won't be using the move A command because the assembler will do that for us. Now one final thing I do want to say, if you are unhappy with the assembler converting things for you automatically, for example, if you want to do self-modifying code, that can be quite important. But what you can do is you can use the no-opt command with VASM, and that will turn off the assembler optimization, and it will mean that it will compile exactly what you told it to. We're not planning to do any real self-modifying code in these tutorials, though. It's not so worthwhile on 68000 systems as it is with Z80. It makes things harder, and it doesn't work with ROM. And because the Genesis and the Neo Geo are ROM-based systems, that's not going to work very well for us. But as I say, if you don't like optimization, if you don't like the assembler doing things to try and second guess what you're doing, then that's something you can do there. So let's have another look at this code now. We've discussed all of these commands. So you can see here we've cleared D0, it's all 0. We've loaded lots of 69s into A0, and we've loaded A1 into D1. Now let's try something else here. Let's do a clear dot B of A1 here. Now you see that's actually failed. What it said is it can't use the clear command on an address register, because while the D0 to D7 are all effectively like the accumulator, the address registers are much more limited with their mathematical options, so we can't do that command on the address register. Another thing we do need to look at is if I just copy this command here and do D0 here and then clear D0 here at the byte level. Now you'll notice that the bottom byte is now 0, but all of the rest of the bytes are unaffected, and this is what I said again before about make sure you know what level you're working at, because if you now do a long level comparison of this register, you're not going to be at 0 even though you just did a clear of that, because you only cleared at the byte level, and if you're comparing at the long level it will fail. Again, we're going to cover this many times because it's so important to 68,000 assembly, so don't worry about it if it's confusing you at the moment. So we've been looking at moving bytes into registers, but of course just moving fixed data into things isn't very good. We actually want to be able to do some mathematics. So now we're going to look at the add and subtract command. Just like the move command, these can work at the long word or byte level, and we're going to look at them at the long level, and we're going to do a simple addition of a fixed value and a subtraction of a fixed value. And we're going to use this new monitor D0 because we're only going to use D0 for all of these commands here. You'll notice we do have some alternate versions here. Add I, because technically speaking the add command should be add I when adding a fixed value to a register, and the same with sub I. But once again, Vasm is kind and it's doing all the work for us if we don't specify it, so that's not something we need to worry about. Again as well, we have a quick version, add Q and sub Q. These only work for 0 to 7 though. We can only add up to 7 with the add Q command, but the add Q and the sub Q command are extremely important. The reason for this is we have no inc and dec commands on the 68,000. These are commands you would be used to seeing on the Z80 or the 6502. The 68,000 doesn't have an inc or dec command because the add Q command and the sub Q command do everything those do and more. We can effectively inc by 2 or even 7, or dec by 1, 2 or even 7 with these commands just as fast as an inc or dec command would have done. So they do everything the other commands did, they were just a lot better. So that's why we have no inc and dec, and that's why add Q and sub Q are so important. But add I and sub I, again, the assembler's doing it all for us, but we just wanted to have them here just as an example. So let's run this and let's see what the result is. So we're only outputting our 1D0 register here to the screen. So we've loaded hexadecimal 15 in at the long level, of course. Then we've added 3, so we've gone up to 18. Then we've subtracted that 3, so we're back down to 15. Then we've added 1, so we've gone up to 16. Then we've subtracted 1, so we're back down to 15. And then we've added 7, which has put us up to 1C. And then we've subtracted that 7 again, and we're back down to 15. So you can see here we can do this maths, and it will just change the registers accordingly. Now, of course, we can do the maths at different levels, and again, this is one of the bits we have to be a little bit careful. So if we just do a different value here, but then we change these all to B, so we just need to change this to a fairly high value. So we'll change this to FA here. Now you can see here we've done our addition and subtraction, and it all looks okay here. But at this point, we've actually gone over 255 being FF, and we've gone back to 0, 1. But because we did the addition at the byte level, the next number along, which would have been in the word level, hasn't changed, because we've effectively treated this as an 8-bit register, even though it's fully 32-bit. Now, this could have been solved if we'd have changed these to an add L and a sub L. Now you can see it's worked just fine. But again, it's important to know how we're wanting to treat the registers and the definition we're going to use. Are we going to use bytes, words, or longs? So if you're confused by all this, if you're panicking and you don't understand it all, I'll give you a really simple solution. Do everything at the L stage and everything will probably work fine. If you don't understand it, just don't worry about it. Do everything with L's and that will make things easy for you. It's just slower. That's the only problem. So don't get too panicked about it if you don't understand it. This is the real technicalities. It's just I want to teach you all of the options. I don't want to lie to you. And at this early stage, I want to give you a small number of commands, but explain them fully. I don't want to be deceiving you by omitting things. So as I say, just like with the add Qs and the add Is and the move A's, Just ignore these if you don't understand them, because the assembler is going to do most of the work for you, and in the worst case is going to be maybe your code's a little bit slower, little bit bigger than it should be, but 68,000 systems are very fast anyway, so it's not likely to be a big problem for you. So we're going to use another command here. We're going to use this program called monitor memdump direct. This will show a bank of memory, and unfortunately we're going to have to use another tricky command, LEA. Now LEA means load effective address. I said earlier that the 68,000 is not like a Z80 system or a 6502 system. It's doing memory management for us. We don't know where our program's going to be loaded in memory and what memory is going to be available to us. So what we're doing here is I've defined a user RAM area, which is the memory according to each system, because it's in different places on every system, but user RAM exists by my definition on all the systems. So we're going to load the 100th byte of user RAM for some testing, and then we're going to show some of it to the screen using this command. Then we're going to load user RAM plus 100 into A0, user RAM plus 101 into A1, and 102 into A2. So A0, A1 and A2 are going to be set to the address of bytes of free memory on the system. And then what we're going to do is we're going to set D0 to 11. We're going to move D0 into the memory address held in A0, so we're actually going to store that hexadecimal 11 into that memory address. Then what we're going to do is we're going to load 22 in hexadecimal into the memory address in A1. Finally, we're going to load hexadecimal 33 into D2. Then we're going to load the data in the memory address of A0, because you notice these brackets, these mean load the address, not the register itself. And then we're going to add that into D2. Then we're going to do the same with A1, load the data in the address held in A1 into D2. And of course we're doing these at the byte level, of course, all these are byte commands. And then we're going to move the result held in D2, because all of these were added to D2, into the memory address in A2 here. And then finally we're going to show the result to the screen. So let's have a look at that. So here's the data before we started. Now the memory address will vary depending on the system, because all the systems have different memory and different options, but the results should be the same. So we started off with some blank memory, and then we loaded our two values in here and here, and then we added them together and we stored the result here. And if you've seen my 6502 series, you'll notice this is basically the exact same example. So let's just have another look at the code, because there's something quite interesting here. Now you'll notice here we filled D0 with the value hexadecimal 11, and then we wrote D0 into the memory address in A0. But in the line here we did that directly. We didn't use any data register, we just moved the data straight into the memory address in A1. And you see 68,000 is very flexible with this kind of thing. We have a lot of different options for the source and destination. We don't just have to, we can load data directly into addresses, into address registers and things like that. We have a lot more power when it comes to how we work with things, and that means that something that can take 3 or 4 commands in Z80 and 6502 can be done with just one command in 68,000, which is one of the reasons why it's so powerful. So let's just terminate this and let's try running this on the Neo Geo as well, just as an example here. So you'll see the memory addresses are different addresses, but the code has worked the same. Now on the Neo Geo and the Genesis, the RAM is a fixed area of the system, so while the system is using different areas, the commands are actually fairly predictable. A more unpredictable one is the Atari ST. Now you'll see here that the memory addresses are very unusual. There's no real, it looks like a completely random memory address, and this is because the area that we're using here has been allocated by the system operating system itself, so we had no real control over it, and this is why we need to really use loaded effective address to load in the address that we want when we're specifying a label within our system. Again though, please don't worry about this too much at this stage. It's going to be something we're going to look at later. It's just I needed to show it you today. If we were going to use this example, I would have otherwise left it for a later lesson. So we're going to go over all of this again in the future. So anyway, we've covered quite a lot of content here today. We've learned about the move command for filling fixed values into registers and for copying registers to other registers. We've learned about bytes, words and longs and how we can work with different register levels so that we don't copy more data around than we need to if we need the extra speed. We've learned about the trickier versions of move and add that we probably don't really need to worry about, that are more of a technicality, to be honest. And we've learned how to store data back to memory using address registers, and how to load effective addresses when we don't know where we're exactly going to be saving to. Now, one last thing I want to talk about is big endian, and there's a nice example here. Most systems are little endian, but the 68000 isn't. Now on the 68000, if you store a word 1, 2, 3, 4 into addresses 0000 and 0001, then 1 and 2 will go into the first address and 3 and 4 will go into the second address. Now that sounds perfectly logical if you've never programmed before, but on the 6502 and the Z80 it's the other way round. The smaller value is stored in the first address and the larger value is stored in the second address. So you would effectively store 3 and 4 into 0 and 1 and 2 into 0, 1. Now again, if that confuses you, don't worry, we're going to look at this again in later lessons. The next lesson is going to be about addressing modes. We're going to look into all of this in more detail with more examples of memory being preset with fixed values, so it's very clear what's going on. But anyway, if you've liked this lesson, please like and subscribe to my channel, because we're going to be doing more 68000 lessons in the future. Also, if you want more, please check out my Z80 series and my 6502 series, because especially if you're looking at the Genesis or the Neo Geo, you're really going to want to look at some Z80 programming, because those systems use the Z80 for their sound processing. If you really want to jump ahead as well, please check out my website, because there's a lot of introduction descriptions of the processor and some commands and some tricks that I've learned over the time I've been researching this system. Also make sure you visit and get the cheat sheet, because that's a quick PDF version of all of the commands the 68000 has to offer, and it will help you out a lot as you're learning. And of course, download the source code for today's lesson, download the development tools that I've provided with the scripts for building automatically, and hopefully you'll be able to have some fun with this at home, and you'll be able to get programming really quickly with this system. Anyway, thanks for watching today, and goodbye.